Hi, welcome to the part 4 series on differential pairs. So in this particular video, we are going to do a deep study on the differential pair bipolar as a BJT version. So up until now, we've seen that the differential pair should have two common emitter stages connected this way, and with the two emitters grounded. But this is a new topology that we've seen here, and we can see that there's a current source tied to the emitters. So we are going to do a quick study on LTspice and appreciate why it's necessary to have the current source tied there. And okay, so let's just jump straight into LTspice. Okay, all right, so I just want to build this from start. Okay, so I'll first place my transistors. So we know we need two transistors BJT, and I would flip it by pressing Control and E. Okay, so the next thing I need is a voltage source here, so I'll press V to bring up a voltage source. And before I forget, I'm going to choose the transistor I'm familiar with, the 2NN transistor. Okay, so what I want to do now is to put a voltage source here as VCC and resistors. So pretty much this completes the bipolar pair. So I'm going to wire it up here. Okay, so I'll place the ground here, a common ground for everyone to share. All right, so let me just separate the ground for the voltage sources and this so it doesn't look weird, since we've not been doing that before. All right, so I just wanted to share the grounds like this, but I just want to keep it usual as we've been doing all along, so you don't feel like the bipolar pair brought up something new. Okay, so up until now, video number 4, this is what we've been introduced to. It's not complete anyway, so I just have to connect this to that. Okay, so I'm going to copy all these, place them right here, zoom out for a little more space. And what I'm going to do different here is I'm going to place a current source. So type current, and this is our current source. So we have so we're going to put 2.5, so 5 milliamperes for a reason, because I have 5 volts here. I'll explain why I chose 2.5 milliamperes. Okay, so after this we'll do an intensive study and it'll make more sense. So let me keep the resistors as 1K each. Okay, so first of all, the bias 0.7, and 0.7. So I'm going to run these quickly. 10 milliseconds and see what happens. So first I'm looking at the inputs, and okay, so I'm looking at let me delete this. Okay, so the input here, we have 0.7 volt as we expected. Okay, nothing fancy yet. Let me all right, so next thing I want to look at is the output voltage here. So that I expect it. Okay, so the input and the output, so it looks like I have, what node is that? That is node 3. So the device is not in saturation. That's that. So let's look at the current. Current is 4.9 milliamperes, and that explains why the device is not in saturation. Okay, so we know what to do. Either I increase the voltage here, or I try to reduce the bias 0.68. I think that should work. I've tried that before. Okay, now the device, let's examine the device voltages. So we know this is at 0.68 and the collector is at 2.4, so it means the device is in forward active mode. So we expect some reasonable voltage here at the output. So I'm going to see the differential output. Okay, so the output here too is similar, same voltages at DC level. Then the current 2.57 milliamperes, 2.57 milliamperes. Okay, so let's go to the differential pair with the current source. So probably I made a mistake here and I biased it with, or my bias voltage changed to 0.7, and we have the same scenario here. So let's see what happens to the device with the current source. And it's still forward biased. Sorry, still in the forward active mode. Let's examine the current. The current is 2.48 milliamperes. 2.48 milliamperes. So approximately 2.48 plus 2.48 should be equal to 5. I'm looking at the collector current going through to the emitter. If I only assume that the collector current is equal to the emitter current, then what we are looking at is, so let me take a screenshot and just explain this on one note. That will be better. Okay, so with this is what is happening here. Because the tail current here, IEE, is equal to 5 milliamperes, is forcing the IC to be approximately equal to IEE over 2, and this also IEE over 2. We saw that they are not exactly the same, and the reason being that the IE, which is the emitter current, that would exactly add up to IEE, but we are only making a very good approximation that these two are the same. Now, what do we notice here? With the previous one, when there was no current source, when I increased the current, the voltage emitter the base emitter voltage to 0.7, the current through the collector was around 4.9, which drove the device into saturation, because that means the voltage drop across this resistor was going to be 4.9 volts, remaining 0. So let me just take a screenshot and explain well here, so you really get what I'm trying to put across. Okay, so this is the message. Before, this value was 0.7, and that meant the IC was free to move to 4.9 milliamperes. You can try that yourself. And that meant the voltage across this became 4.9 volts. So the voltage at the emitter became VCC, which is 5, minus 4.9, and that was left with only 0.1, driving the device into saturation. But with a current source, so if I had a current source here and it was fixed at 5 milliamperes as we did before, then even if this base emitter voltage increased to 0.7, the collector current would not be allowed to increase that much. The collector current is limited by this 5 milliamperes. So the maximum collector current I could get would be 2.5 milliamperes. Once again, I'm assuming that the collector current is equal to the emitter current. So 2.5 milliamperes, 2.5 milliamperes. So even if I increase this to 2 volts, so let's see what happens with the current source and without the current source. Obviously, we have an idea what will happen without the current source. But with the current source, I'm going to increase this common biasing voltage to 2 volts. And I'll run the device and first check the node voltages. And surprisingly, my node voltage says the device is still in forward active. Okay, so let's do without a current source and see what happens. Okay, so without a current source, the node voltage I'm reading from down here, I'm not sure if you can see from your screen, is 39 millivolts. So obviously the device is in saturation. But with the current source, even if I increase the VBE, the device is forced to have a collector current of 2.5, making this. So this means in setting our headroom, it becomes very easy. So let's do other examinations and see. So number one, I'm going to inject some noise into the VCC and see what happens in both situations. So I'm going to bring another voltage source, rotate with Control R, and it should be in series. Control R. Okay, so noise with maybe 2 milliamperes and frequency of about 10 kilohertz, so very noisy. Okay, let me make that 5 so we can see it more clearly. Okay, so I'm going to run this and see. Node 5, what did I take out? Something is not defined, voltage. Okay, this guy here. So I did 5 milli as noise with 10 kilohertz. Okay. Alright, so this is a very noisy, so just to see the VCC in both cases are very noisy. So let's see how it affects the output here. All right, so the output here is already in saturation, so I don't expect anything meaningful. But let's see the output here. All right, so at least there is an output. Okay, so let's just be fair and let's take this one out of saturation by putting, we know if I have 0.68 as the base emitter voltage, then the device will not be in saturation. Okay, so I've done that and I'm going to run. Okay, so we have very noisy output. Even though there's no signal, we just expected a straight line. So we are going to see the differential output for both cases. So the advantage that we've seen here is that the mirror current source here limits or give straight values to what the base emitter voltage would be. So even if the bias voltage failed us, we will still have a defined base collector current that will be half these values. But let's just jump into what we really want to do. So this is node 2, node 7, and this is node 6. So I'm going to find the differential output. So the differential output is going to be node 7 minus node 6 minus node 6. I just double clicked on that and now write 7 here. Okay. That wasn't very nice. Actually node 6. Okay, so actually node 5 minus node 6. Okay, so I wasn't expecting that. So I'll change that to node 5. So when you put you see the node number. Good. So you see the error is cancelled out. That was flat line. And the noise has been rejected without the current source. And with the current source to down here, let's see if there's any trade-off. We call this node 7 and we call this node 8. So I'm going to do node 7 minus node 8. I'll just copy this minus and change this to 8. So this is going to be the differential output. Okay, so the noise in the VCC has been rejected clearly. So now let's make it interesting by placing an actual signal. So you know that this signal should be a differential signal, otherwise it will be rejected by the input. So if I place a microphone here, so I'll call this mic, and we know our definition of the microphone signal, a sinusoid with 10 millivolt 1K as we've been using all along. So that's our signal. It doesn't have to be a microphone, the signal I want to amplify. Okay, so if I place this signal, so M to move it, and I place this signal here, what I've done is so I'm tapping the differential input from above the bias voltage. So after the bias voltage, I'm going to add the differential signal. So the differential signal should look like this. I'm going to copy this guy, Control C, put him here. Okay, so as it stands, there are no differential signal. It's the same signal I've copied. So both inputs are going to have the same signal. So let's just see what will happen. So there's still no differential output. This I've not. So this is a 6 and 5 node are these two nodes. Okay, so I'm going to get a differential signal here by just putting negative in front of this guy. And let's run and see. And there we go. We have a differential output But let's see the single stage output. So this single stage output, okay, so you have that, but our noise is not visible enough. So let me just try and raise the noise level so we can quite see it. Okay, so now clearly we can see the noise in the single stage. And if I check this side too, I will see the noise. Okay, so this is the input output from this single stage and output from the other single stage. So you see the output signals are also differential signals, and the difference between them, we have that. Okay, so I just want to copy my current source and put it here. Okay, so without the current source, let's see if the signal bias messed up and raised to 0.7. Let's see what happens to, so we have some headroom lost, and surprisingly our rejection to the differential signal was even surprisingly not met. So we are just going to place the current source. So I'll just copy this guy rather than just rebuilding that circuit here, that will waste time, and put him here, and let's see if that helps. And guess what, it helped. So that tells us how robust the differential pair becomes with a current source. So the current source will predetermine the voltage at the current through each side of the pair. And even if we mess up with that to go as high as 4 volts, that might be extreme, but okay, obviously that was extreme. 4 volts, we are looking at currents of around 10 raised to the power 50 amperes. So that's extreme. So let's do something reasonable like 2 volts with a current source and see. And we have, so we are still taking notes. So this V node 6 minus node 5, that's node 5, and this node 6. So the differential output is still clean. And I wonder, okay, so that's the current. We don't want to see the current, so let me just delete it out. So now we have seen the robustness of a differential pair by placing the current source in between the tails. Okay, so we end this video here. In the next video, we will analyze what really happens there. Bye.